Welcome to this installment of the Secure Your DNS, Secure Your Network series. My name is Tim Rooney, Director of Product Management for Diamond IP. The goal of this video series is to break down into bite-sized chunks the myriad ways the domain name system, or DNS, can be attacked or manipulated for nefarious purposes. Now in this case, today we're going to look at how you can use DNS to actually help defend against malware attacks. So when we talk about malware, we're talking about malicious software that runs on a compromised system without the user's consent. So the objective of a malware author in infiltrating your systems might be to disrupt the network, might be to snoop, gather traffic, information, exfiltrate or steal that information from the organization. Maybe it's personal financial information, maybe it's corporate sensitive information. Also, it can be used to persist within a network to vary the activities. Through communications with a web-based command and control center, the malware can actually communicate, get updates, get instructions, and perform various activities that can be programmed over time. Demand payment, of course, through ransomware or crypto mining, actually leverage your computing resources for crypto mining, and without perhaps you being aware of that. But certainly can be expensive in terms of power consumption and loss of performance on your own computing resources, especially if you have it running in cloud environments. Malware comes in many forms, as we'll see. We'll take a quick sample of that, and it can persist stealthily on a system indefinitely if it's not detected and eradicated. And as I mentioned, malware can also contact its author website for instructions, code, and also to transmit sensitive information. And according to AV-Test, over 1.3 billion malware programs have been identified. And there are about 450,000 every day identified. So quite a dynamic, unfortunately in the bad way, industry in terms of the proliferation of malware and its impacts on organizations. So just a quick sample in terms of malware's really infiltration span. Targeting the mass gamut of really any type of OS, any type of device, through Trojans, getting access through the back doors, etc., through hidden means. Ransomware, we've seen this really across not only end-user devices, really back maybe in the late teens, 2000 teens, into more really enterprise-based attacks more recently through the meatpacking industry as well as pipeline, and then also even through municipalities. CPU level malware, there's malware to attack your computing level resources. Internet of Things botnets, so IoT botnets really have been used in the past to really enable organizations, malware authors, to infiltrate IoT devices like your security cameras, intelligent smart home devices, etc., and use those as a launching point for denial of service type attacks, as was done against the DNS organization in 2017, or for other purposes to really try to disrupt a target's network. And then again, cryptojacking, so really using the resources of an organization to really help with the mining of crypto. Delivery mechanisms, the old worm, really the first form, still in prevalent use. Trojans, as I mentioned, email attachments, so people clicking emails and unwittingly installing malware. Websites, just clicking on links there, and also installing malicious software. File sharing services, cloud services, removable media, scareware, bring your own device. It's a variety of ways that malware can be delivered to end user devices, so really caution is certainly warranted there. Let's take a look at how malware might infiltrate a device. And in this example, we're going to look at a BYOD, or bring your own device example, where malware gets infected kind of off-prem, off the enterprise network. But this could just as easily be done within the enterprise network if a user, for example, clicks on an email attachment linking to a malware site that can install its malware on the user's computer unwittingly. But in this case, the user has the malware installed, they bring it into the network, and now the malware activates within the computing device and attempts to locate its command and control center, and it's going to pretty much use DNS for the most part to locate that command and control center. So DNS provides a convenient way. It's ubiquitous. Every IP network has DNS servers. And using the resolver configuration on the computing device on which the malware has installed itself, it can easily use DNS to locate the command and control center. And it also enables the malware author to change their IP address. Should their IP address be detected and blocked, they can always just get a new IP address and use the same domain name, or even use dynamically generated domains, or DGAs, to kind of create even a moving target on the domain name level side. But that's a different video altogether. But basically, using DNS, the malware can locate and connect to the command and control center, again, to get instructions, software updates, exfiltrate information, etc. So how can you mitigate the malware? User education and training certainly is very important. Make sure your users aren't clicking just any email attachments. Having antivirus installed, certainly, and performing regular scans. Multi-factor authentication to secure access to devices and servers and systems. Data backups, just in case there is an infection that requires the ransomware, for example, going back to a known state. Keeping current with patches and updates. Password policies, again, to keep systems secure from an access perspective. Filtering network traffic, good idea in terms of just looking at what's going on in the network, and then also being able to block from a firewall perspective, for example. And then also from a DNS firewall, and looking at how DNS can be used from a firewall perspective to help protect your malware. And this is really where we're going to focus the rest of the presentation, primarily around the DNS firewall. And really, a DNS firewall adds to a layered security approach, or a defense in-depth approach, where you're looking at the device level antivirus, for example, and the network level firewalls. Well, DNS, as I mentioned, is always really, for the most part, the first step in any IP communications, whether it's malware or your devices. So looking at the DNS layer give you another added chance to detect the malware before it comes into play. But just stepping back for a moment, looking at just general DNS defenses. So for attacks against DNS itself, certainly you want to protect against that. So we'll just send a little sidebar here in terms of some of the key areas you should focus on for your DNS servers. So server security, certainly hardening your operating system or using appliances. Authentication, changing your passwords, the default vendor passwords, for example, setting permissions where that's provided. And also physical controls is very important in auditing of access logs and what administrators are doing. Deployment approaches really look at a role-based approach. So keeping the servers focused on specific roles, whether it's just for recursive access in terms of accessing the internet for your end users to resolve internet queries, or authoritative, internal and external, making sure that that authoritative data is only available for the audience for which it's intended. Then also with redundancy, making sure that there's high availability. Clearly, as the first step in IP communications, DNS is critical, so having that highly available through redundancy is key. Denial of service attacks, really prevalent on really any type of protocol, so inbound and outbound rate limiting is important. Anycast addressing can help to spread the attack across multiple servers, sharing a common IP address, query quotas, and similar things that your DNS implementation can provide to help with DOS, as well as network protections in terms of ingress filtering and also just quotas on general network traffic. And then DNS protocol security in terms of various allow query, for example, type of ACLs that you can set at the DNS level adds another layer of defense for your DNS servers. But if we take it now a look, let's drill back more into malware again and look at this situation that we talked about, where we're now going to impose a DNS firewall and look at how this case with malware infestation, again from a BYOD device in this example, but it could be really any type of infiltration within the network or outside of the network. So once the user's in the network, the malware activates, let's say, and now again, like before, attempts to use DNS to make the connection. But in this case, our DNS server is equipped with a DNS firewall configuration, or response policy zone, as it's called, and is able to identify that that command and control center domain name or IP address, or the name server from which it's being served, is known as malicious or potentially malicious, and therefore the query can be blocked. or the user could be redirected to another site, for example. We'll look at all the various triggers and policies a little bit later. But really the bottom line is, at the first step of the communications, your DNS server in this case can nip that in the bud and prevent that communication from happening. If it does get past DNS, hopefully your firewall can detect it, or the malware, anti-malware on the device. So you've got, again, those layers of protection give you just that added opportunity to detect and prevent malware proliferation. So in this case, maybe your firewall wouldn't have caught this situation if that was able to resolve and get to that command and control center, and maybe the antivirus wasn't up to date yet. So again, that DNS adds another layer of protection to prevent malware from infiltrating and spreading within your network. So really, in terms of why DNS firewalls, again, adding that layer, that defense in depth capability to allow you to filter DNS queries on domain names that are being queried, on the IP address of the who's doing the querying, and also the IP address of what's responded back in the answer. So there's various reputations of IP space throughout the internet, and that information can be used as well based on the resolved IP address, and also on the name server that's responding. So certain domain registrars using certain name servers can be a variable reputation, which can also be applied to your DNS firewall. The firewall feed focused on these other areas of DGAs, dynamically generated algorithms, which are really the dynamic domain names I mentioned earlier. Fast flux, another form of dynamically generated domains and name server addresses, and also phishing domains. That can also help add to your defenses. Having multiple feeds, certainly having multiple, again, like aligned with the defense in depth approach or the layered approach, having not only a DNS firewall, but a firewall with multiple feeds can provide added perspective as well to deepen the defenses there. And then having frequent feed updates certainly is key, because again, this is a moving target. It's continually evolving, so having that be performed dynamically through incremental zone transfers is core. And then of course logging the offending queriers, those devices that could be perhaps infiltrated with malware, so that they can be remediated quickly. So if we look back at, okay, well, how does this really work on the DNS server itself? So I've got this recursive server with the DNS firewall feed, so I configure it really for what's called response policy zones, and that really defines on the server, it says, well, look at these response policy zones whenever we're resolving queries, and provide a policy if it meets the trigger. So in this case, my end user device is querying for bad-example.com, and that happens to have a trigger in my response policy, bad-example.com. So you see the result I get back from the authoritative bad-example.com DNS server in the lower right is 192.0.2.54. But I've got a response policy for that name that basically maps the address to 172.16.100.1, and maybe that's an internal web portal that that user is being directed to for remediation. So this is an example of a QName match on the badexample.com, and then really a rewrite or local policy of defining or rewriting that response to a different IP address. So that's just one example of the ways that the response policies can rewrite DNS response information. So let's take a look at some of the other ways. First, looking at the triggers, what can trigger a DNS firewall policy. Really the QName, we just saw that in terms of the query domain name example. The IP address that matches the IP address in the answer. So basically, you're querying for a given server out there and you get an IP address response. Well, that might be suspect for whatever reason. So you can define that in your response policy zones using this RPZ-IP suffix, really the top level domain in essence. It's kind of like the INAT or ARPA zones, where you would just reverse the IP address, including the CIDR address, the CIDR length as the first octet there, whether it's V4 or V6, and then followed by the IP address reversed, and then the RPZ-IP suffix. And we'll take a look at some example resource records as well. And really these policies are defined as resource records, the language of DNS. So it's the special encoding of these within response policy zones, and we'll talk about the configuration also in a little more detail later. rpz.nameserver-IP. So again, you can trigger on the IP address of the name server that's responding. Maybe it's from an address space that's suspect. Likewise, the name of the name server that's responding, you can also trigger on that. And also the client IP address, the device that's issuing the query itself, so you can apply policies based on given source query addresses. Now, in terms of meeting the trigger, the various policies you can then apply, you can reply with an NX domain. So basically, you're rewriting the answer that you're getting from the authoritative server with, in this case, an NX domain, which is basically a dot in the data field of the resource record, and we'll look at, again, examples in a moment. No data, basically saying, well, okay, that domain has no information on it, that domain name. And so that would be a star dot in the data field of the resource record. Pass through, this is basically just a note that it triggered. Perhaps if you have logging set up, it'll log that, and it'll basically pass that through unmodified. Drop, so in this case you don't even respond to the client, and that's kind of the case where we looked at initially with the DNS firewall, with the malware infestation bringing the device into the network. There's no response given. The TCP only, this basically sets the truncated bit in the DNS header to install the client to retry using TCP. And then local policy. This we saw in the earlier example, where you can basically rewrite the answer into a local IP address, for example, as we saw before, so that you can redirect that client accordingly. In terms of some example records, so the first one here, bad-example.com, cname type, and dot is in the RData portion. So this is what I was referring to earlier in terms of what goes in the RData is really the policy you're applying, whereas the name or the owner field is the trigger in this case. So I've got badexample.com, and then I've got the subtree, star.badexample.com. So you don't, another point is don't add a dot to the end of the badexample.com dot. So a lot of times in zone files you can have a fully qualified domain name, but in this case you should not do that. Leave it unqualified there, but if you want to block an entire subdomain, you should include both records, the domain itself and then the star dot domain, to block the entire subdomain. And in this case, applying the dot as the data field is the NX domain response. The star dot after the CNAME here is the no data response. So any queries for, in this case, we're using the IP address of the answer 192.0.2/24. You can see how that's encoded with the RPZ-IP top-level domain, so to speak, on the owner field. And then the policy applied to that trigger is the star dot indicating no data. Here we have an example of the drop. So I'm doing a trigger based on the name server name and the name server IP address, just two examples here. You can see how the IP address is likewise with the RPZ IP is reversed, and the also with the CIDR length as the first octet there. And then the RPZ-drop dot is the drop policy, so that is in the data field of the resource record. And then the TCP only, likewise in the data field, is applied, and here we're looking at the client IP address trigger on the left with the resource record, and again that's the IP address is similarly formatted, so that is triggered by the client IP address, and then the RPZ TCP only indicates to force the querier to use TCP. Then here we have badexample.com, and this is the example we saw earlier, where I'm basically doing a local policy to rewrite the answer, whatever I get back from the authoritative server, and just rewrite it as the 192.168.0.1. So in terms of defining the response policy zones, so you've got these zone files, they have these resource records encoded in this special format, and therefore they're response policy zones. So they're really policy zones. They're not really resolving per se, but they're really consulted by the DNS server to apply these policies on triggered resolutions and queries. So first you would declare the response policy zones in the DNS configuration, and we'll take a look on the next slide about how that's done with bind 916. And then for each of these response policy zones you have, of course, it is a zone file, so it does require a start of authority and name server records, so you can define those there. And then also the individual policies are defined as resource records within the zone. So using the examples we just looked at on the last slide, you would populate your zone files with these resource records, which encode the trigger and corresponding policy for each. And of course, if you're using a DNS firewall feed, you can basically just receive this information through incremental zone transfers. Again, it's a zone file using standard zone transfer communications to update that in your real time. So let's look at a response policy zone declaration in Bind 9.16. I'll highlight some of the differences from 9.16 from 9.11, the last extended support version of Bind. So in its simplest form, you would just define response policy statement with zone and the zone name. So this is the name of your response policy zone that's on the server, and it's going to contain these resource records that indicate my policies. Now, you can also define for that zone particular options. So the policy, you can kind of overwrite this. Now, policy given, basically whatever in the zone file. So that's the default. Whatever's in the zone file as those various triggers and policies, just use that. So it's kind of superfluous to define policy given, but it is an option that can be overwritten. Disabled enables you to disable the response policy processing for that zone. So any of the triggers that are met, they won't be applied. Pass through, basically pass through everything. So this might be useful for initial testing. Drop everything. You can have it apply a drop policy on that zone. Also to respond with NX domain, no data, TCP only, or CNAME with a domain name, where you can redirect or apply a local policy for all of the triggers that are matched in that zone file. So this policy sub option gives you the ability to kind of define a blanket policy for that zone to enable you to do some troubleshooting, some testing, etc., or to modify responses on a blanket level. You can also define whether to apply the policies to recursive only queries, so the recursion desired bit set. Typically is the case, but if you have a server serving up authoritative data as well, maybe with some private address space that you don't want to resolve on the internet, you could set that to no and have it apply on authoritative or non-recursive queries as well. Max policy TTL, so the length, the duration of the existence of the policy, you can set the max there for the zone, whether to log or not, yes or no. And then we recommend you set that to yes. Then there's some other options that were added in 9.16. Add SOA to the authoritative section to indicate that you can kind of keep track to the serial number of any changes to the zone. Your min update interval is going to be the minimum amount of time that the zone is updated. So you could be getting incremental zone transfers every 5 seconds, but if you set this to the default of 60 seconds, the server won't apply those defaults except on an interval of 60 seconds. So that's kind of your minimal interval for updating your response policy zones based on incremental updates. And then the next two options enable the name server IP and the name server domain name triggers. So you can basically define those on a blanket basis to set those as yeses or no within the file, within the zone rather. Now you can also not only define these policies on a given zone, and you can have, with Bind 9.11 you could have up to 32 response policy zones, so you could list 32 zones here in the statement, and with Bind 9.16 it's actually up to 64. So you could have 64 zones in this response policy statement, and each could have its respective options. Now you could also set options on a blanket basis for all of my response policy zones. So these same type of options we just reviewed, you can set the recursive only to yes or no, the max policy TTL. The next option, break DNSSEC, yes or no. So basically, with you're changing answers with a response policy. You're rewriting responses. You're sending NX domain, or you're sending a different A resolution than what was queried from or what was received by the authoritative server. So whenever you change something in the response, by definition, you're going to break DNSSEC, because really the value of DNSSEC is to provide that data integrity validation in addition to the authentication. So you need to set that up to either yes, you acknowledge you're going to break DNSSEC in the response, or no, where it will not. If it does change DNSSEC, unless it's a pass-through type options or drop, for example, it won't perform that function. So that gives you the control there at the blanket kind of cross RPZ level, cross zones. The minimum name server dots. So basically within the domain name being queried, you can set the number of dots or the number of labels that are required. Labels are dots plus one, basically. So the default here is 1, meaning that it doesn't check for TLDs, so .com. It's not going to check for a .com query, but it might check for xyz.com or example.com if it's set to 1. If it's set to 2, it wouldn't check for example.com, but it would check for www.example.com. So it's really the number of dots, not counting the trailing dot, the root dot. So that's really what that applies to. So if you can kind of control the depth on which you want to apply your response policy checking. QName wait recurse, this actually indicates, now when you get a server gets a query, it's going to know what's being queried right away without actually resolving the query. So in the general case, response policy zones, response policy, they typically perform the whole resolution process and then apply the policy. Now, the wait recurse options for just the QName being queried and also the name server IP, if I have that in cache, you can indicate that you don't want to wait for the recursion. So you can set that to no, and then as soon as I get a QName query, I can respond with the corresponding policy that's assigned for that QName. So this just gives you a way to kind of improve the performance relative to those given QNames or name server IPs if you desire. Just an option there you can set. And then the other options we talked about, add SOA, min update interval, and SEP enable, and as name server DName enable. And then the last two options here relate to using in the API for your response policy information. I think Farsight Security, for example, provides an API where you can define, have the server query the API on a query basis. So the DNS response policy service, enable, yes or no, and then once you enable it, you can define options that are going to be germane to the service that you're using. So that's really what those last two options apply. And again, they would apply to all of the zones that you define in the response policy statement. So you can see this is a rather complex statement block within your zone file, so be careful when you're configuring that. But certainly to help you, you can either do this manually using that response policy declaration, as well as all the individual resource records. You can also leverage an IPAM system that we happen to provide to help you with that, and we'll take a look at that in a second. And then leverage services such as, there's a lot of open source and also for pay services out there. Diamond IP offers a service as well. So to provide incremental updates, incremental zone transfers for response policy zones. And then you can use multiples of these, again, because you can have up to 64 in a 916 server of these zones. So each service would really correspond to one or more zones on your server. You might have an allow list zone defined to allow certain known good domains and IP addresses, etc., to go to pass through or apply policies to, and then you would have your response policy services, the block type of services after that. So that's one thing about the response policy statement, is that the order of your zones are important, because that's the order they will be loaded in and processed. So make sure you put your allow zones in the beginning of your zone declarations there on your response policy statement, because once the zones are really loaded into memory, they're basically canonically ordered, and so you lose a little bit of that control that you would otherwise have. So that's why the ordering of zones gives you that level of control. So you can leverage these services, kind of just make sure you order them in their proper zone response policy zone statement. And then you also want to configure logging. So it's very important to be able to identify when a response policy is applied and the answer is rewritten. So either through logging, through the statistics as well. You certainly want to keep track of that. And we also happen to have an appliance to enable you to keep track of that and monitor that and maintain a history of that, as we'll talk about in a sec. So the Diamond IP DNS Firewall solution. So certainly in your response policy statement, here's a quick snippet of our user interface. So you can basically provide a graphical interface. It's tabular, so it's easy to enter, easier at least in terms of the complexity of the option. So all the sub options are listed there. You can also define your logging quite simply through the product and expand that and apply that to multiple servers. Define it once, apply it multiple places. You can configure your zones. We have an RPZ wizard, so you can define each of your feeds through the wizard process. simplifying that process. Of course, we offer a DNS firewall feed ourselves as well, if you'd like to subscribe to that. And then our Sapphire A30 Auditor appliance is an appliance that really enables you to aggregate DNS transaction data and log event reporting. So all the Sapphire DNS, that's our appliance, all the Sapphire DNS transactions are basically sent to the auditor for reporting, for detection of anomalies, and also all the log events in terms of the RPZ trips are also reported there, so you can detect when these situations arise that could spur pending investigation and also troubleshooting. In addition to our DNS Firewall service and our IPAM Auditor product, we offer a number of other capabilities. On the left side, you really see a number of the ISC bind capabilities that we provide. Again, through the graphical interface, you can set up all these various options. Really, all the options that bind supports, we support in our graphical interface, just through a simpler way to enter as opposed to editing a text file. So it provides a very streamlined process for you. And again, you can apply it across multiple servers through our DNS Server template feature as well. So ACLs, Anycast, update policies, control channel, and stat channel ACLs, etc. are all provided. Our hardened appliances available as hardware or as virtualized on private clouds, VMware, Xen, Hyper-V, KVM, and also public cloud services such as Azure and AWS and Google coming soon. And then we also offer DNSSEC appliance, so basically being able to, on the authoritative side, automate the signing process, key generation, key rollover, updating of the child DS record, so automating the chain of trust updates when you roll your KSK, for example, if you're familiar with DNSSEC. And then also on the recursive side, setting up the validation there with the trust anchor management that's automated through the root zone. As the root zone changes keys, your recursive servers will pick that up and automatically update that trust anchor so that the entire domain space that's signed up to the root can be validated with DNSSEC. So Diamond IP offers a variety of DNS security features to enable you to better secure your network overall through this variety of mechanisms to help you secure your DNS and secure your network. If you'd like more information, please visit our website at diamondipam.com. I've got my own website, ipamworldwide.com. I invite you to visit as well, or you can email me with any particular questions that you might have. Thank you.